So, good morning to one and all again. So, let's begin with our next session. In the previous session, we tried to calculate about the various values of cell and how the cells are converting into modules by having number of cells connected in series for the particular PV module. In this session, we try to emphasize about the module. Means, say for example, in the last class or in the last session, we have connected number of cells in series for the preparation of one module. In such a case of the number of modules that is to be connected with the series and parallel connection for having higher number of wattage output. See, if you connect number of modules in series or in parallel, the power will always increase. But as the climatic condition will be changed, depending upon that climatic condition, the power output will be variable in nature. So let's begin the design. Before we proceed further, I'll start from the same design. That's what we have done in the previous video lecture series. So why this example is again important, because this typifies the SPV, that is solar photovoltaic module. It is having the particular meter square area. See, if you can consider the cell area, it is in centimeter square. Over here it's a meter square, so it's a module. It has a current at a maximum power point is 7.83, that is IMPP or IM, and the voltage at maximum power point is of 29.4 volt. So the short circuit current of the module is 8.52 ampere and the open circuit voltage is 36.7 volt. And we need to find out the fill factor, maximum power point and efficiency of the solar cell at STC. In the maximum power point, we need to find out the power at maximum power point. So if we need to multiply this Vm into Im directly, we will get the maximum power point. Again, the fill factor is the highest rectangle, that is dim fit with the solar IV curve. It is the ratio of the multiplication of maximum current and maximum voltage, means voltage and current at MPP point respectively for particular radiation. It is nothing but PM divided by ISC into VOC. So the fill factor is 80.10%. Now talking about the efficiency of the PV, it is the ratio of P out upon P in, that is maximum power, divided by input power into area. So ultimately you get the P in at 1000 watt per meter square, that is the input radiation. If we can convert into power, we need to multiply the same with the area, so I get the highest possibility of the power. So the meaning of this efficiency means that if you can consider the per unit, in the per unit it is 1, and it is, in the case of percentage, it is 100%, then among 100 of photons, only 15.46% photons are useful for the generation of the electrical power, and after consumption, generation of the electrical energy is the appropriate word. So let's begin the thing about the modules. So if you are considering the number of modules to be connected in series to obtain maximum power point voltage of 70 volt, so we need to connect a number of modules in series such that the series connected modules can obtain a maximum power point of 70 volt. The modules available for the connection are having the following parameters. So these 4 parameters we have. Now we'll go again with the stepwise. Step 1, note down the voltage requirement. Our voltage requirement is 70, that is 70 is not VOC, it is VM. but VOC is not given, and A for the array. So VOCA is the open circuit voltage of the array is not given, but the module voltage is given, that is 15 volt, and we need 70 volt from the array, that is requirement is given. Step 2. Now we need to note down the parameter of the PV module or a module such that it is to be connected in series, meaning similar parameter of the PV are connected in series. So this is what the input is given. From the given input, if I multiply this 15 and 3.5, you will get 52.5, that is maximum power of PV module, or this point is also known as MPP. In the third step, we are estimating the number of PV modules to be connected in series. In that case, our PV module power will be obviously increased. So the PV module parameter that we are going to consider is the requirement of the array voltage, voltage at the maximum power point from single module, that is 15. So number of modules in series will be NS equals to required PV array voltage at maximum power point VMA divided by VM. So if I divide it, I get a fraction of 4.66 module, which is not possible physically. So I will go for the higher side, that is 5 modules. And the current from the PV array is the same because all the modules are connected in series. So the upcoming figure shows the 5 identical modules are connected in series for getting desired amount of voltage and the current respectively. So this is what the outcome. Now estimating the total power now. So obviously the voltage will be 15 into 5 now, so 75 volt. Obviously if you want maintain the 70 volt over there, it might be a regulation, or you may go with the closed loop control. In the second case, here the array voltage is 75 volt, which is higher than the requirement of the 70, so it can fit. This is the second option. The second estimating series connected module estimation is the current. Over here the PV array current there is a problem in the unit, it's ampere. Then maximum power of single PV module is 52.5 watt. The number of modules are to be connected in series is 5. So if you can multiply 52.5 into 5, in that case we'll get 262.5. That is the total power at STC. And second case, a parallel combination. In previously we need to go for the system requirement of voltage, over here system requirement of current. We need to estimate the number of solar photovoltaic modules to be connected in parallel to achieve the current at peak power point of 42 ampere. The system voltage requirement is the 16 volt. The modules to be connected are having parameters of given. So now we'll go again step by step. Need to note down the current requirement first. Again in the same of the previous example, in this case the short circuit current of array is not given, but the current at MPV point of PV module is given, that is 42 ampere from the array. Now we need to note down the same parameters as what we did over here, and we'll try to calculate the PM, that is 112 watt. Now estimating the number of modules to be connected in parallel. Previously we have connected in the step 3, estimating the number of PV modules or springs to be connected in series. Now as we are considering the parallel connection, over here number of modules are connected in parallel fashion, 1, 2, 3, 4, likewise up to n. So the required PV array current at maximum power point is IMA, that is 42, that's what we want. Current at maximum power point from single PV module is 7, 42 by 7 is 6. As all the modules are connected in parallel, the voltage remains same, that is 1616 volts. So in the step 4, we are connecting the total, how much load that one can connect, means estimating the total power. So the PV array voltage at maximum power point is 16 volt. PV array current at maximum power point is multiplication of number of modules, that is 6 into 7, that is 42. Again there is a mistake, over here it's the ampere. Then maximum power of single module of PV module similarly is 112 watt. Then PV modules to be connected in parallel is 6. So in the previous case we are considering this 112, it is for the single PV module, and if you can convert it into string, then such 6 modules is required. Then if you multiply this 112 into 6, you will get 672 watt. Similarly, we can bifurcate this PM with VM into IM or VMA into IMA. So in that case, your NP would be incorporated with the IM into NP, that is nothing but IMA. And over here, my VMA is same as VM, so you'll get 672 watt. And this is what the connection of all the 6 modules connected in parallel for generating 16 volt and 42 ampere. The kind of question can be asked in any examination or any competitive exam, how we can produce the maximum current by connecting number of modules in parallel and more voltages by inserting number of modules in series. So next segment is the mixed combination. So now we'll go with the estimate of number of PV modules to be connected together in order to design solar PV system for power generation with the following requirements. So the power equals to 10 kilowatt, voltage at peak power is 200 volt, current at peak power equals to 50 ampere. The PV modules available for the plant are having following parameters. Only VM and IM is given. We need to recalculate the number. After calculation of number of PV module, estimate the actual peak power of the system. So in this case we'll go with the mixed combination. So peak voltage and the current requirement of PV system is higher than the voltage and current of the individual modules. So it is required to connect PV modules in series to get higher desired voltage and parallel strings to get higher desired current. So the following procedure we will go. Again we will go step by step. Again PV module parameter. So what we need to do, we need to go for the peak power requirement of 10 kilowatt. So that is what the requirement of 10 kilowatt or 10,000 watt. So PV module array open circuit voltage at peak power. It is given here, but one can also calculate if IMA is known. So your VMA is 10,000 divided by 50 is 200. That is the peak power current is given. 200 volt. Similarly, the module current is 10,000 divided by 200 is again the 50. Step 2. In step 2, we are having the module parameter, only VM and IM is given. So each module at a given radiation will generate 297.5 watt approximately. So estimating the number of PV modules to be connected in series and parallel. So the required PV array voltage at MPP is 200 volt. The voltage at a maximum power point of the single PV module or a string is 35 volt. That is given over here in the problem statement. So number of modules to be connected in series is VMA, that is 200, divided by Vm is 35, that is 6. Similarly, the current is 50 ampere, then the current and maximum power point of PV module or a PV string is 8.5. So again 50 divided by 8.5, so 6 modules are required. Now the estimating the total power. Now from the first 3 steps, we can compute 6 modules are connected in series and other 6 modules are connected in parallel. So after having this concept, what is the new value of the array voltage? That is, initial voltage Vm is given into 6, so you get 210 volt. Initial current 8.5 ampere Im is given into 6 is 51, that is ampere. So the maximum power of single PV module is Vm into Im, that is 297.5, also computed earlier. So with having the same thing, if you have maximum power of PV module for entire array, we should multiply this with the individual number of PV modules requirement, and we are considering this PM, that is 10,710 watt. So this is what the entire connection 1, 2, 3, 4, 5, 6 and 6 36 modules are connected in series and parallel combination to achieve desired amount of the voltage, current and hence power, and each string has this parameters with us. Now if we can increase the capacity of the PV power plant from 10 kilowatt to 1 megawatt, then how much modules are required? So this is the last problem of this session. So we will go a step by step for the same. So designing the number of PV modules to be connected in series and parallel for 1 megawatt P means peak power of PV plant, as PV will generate the DC power. So in PV power plant, the desired voltage at maximum power point is 700 volt. Estimating the current peak power point of the plant, estimate the peak power that will be supplied by one such PV module string. The parameters of PV modules to be used in the PV plant are following. So it is given. Now we will follow the same procedure over here. The rating is 1 megawatt, VM is 700 volt, IMA we are considering this approximately 1429 ampere. In step 2, the module parameter is given, VM, IM and PM. In step 3, we are going to have the 700 required PV array voltage and the maximum power point voltage for the single module, likewise for the estimation of the current. So we are considering number of modules to be connected in series is 22 and the number of modules connected in parallel in this case is 191. So in step 4 we will go with the same thing. That's what we have done in the previous numerical. Over here the new value of PV array voltage is VMA. So VM is 32, which is given, into 22, that is 704 volt. Similarly for the current and similarly for the power. So the maximum power of PV module array is ultimately this 240 into 22 into 191. That is, in this case it could be a multiplication of 704 into 1432.5. So in that case, if we are considering this 704 multiplied by 1432.5, we will get 1,008,480 watt. That is around 1 megawatt hour. So with this we can complete our session on the designing of PV module. I hope you have enjoyed the same. Thank you very much.